Inverse trigonometric functions. In this section, we'll take a quick review of these types of functions from what we learned in a trigonometry course, and then we'll see how we can apply calculus concepts to these types of functions. So from trigonometry, we have these facts regarding the inverse trigonometric functions for the sine, the cosine, and the tangent. For y equals sine inverse x, or y equals arc sine x, we know that the domain of this function is from -1 to 1, and its corresponding range is from -π/2 to π/2, and we have the related inverse properties. That sine inverse of sine of x is x, as long as x is between -π/2 and π/2, and sine of sine inverse x is x, as long as x is between -1 and 1. And you may also recall that the way we can think of working with this function is what is the angle that provides a certain value. So if I asked what is the sine inverse of root 2/2, this is asking us what is the angle, in a sense, what is the real number on -π/2 to π/2, whose sine is root 2/2, and of course that's then π/4, because the sine of π/4 is root 2/2, and π/4 is between -π/2 and π/2. And we have similar statements regarding the cosine inverse, or arc cosine, and the tangent inverse. Things to remember are that for the cosine inverse, its range is 0 to pi. And for the tangent inverse function, its domain is all real numbers, and its range is -π/2 to π/2, non-inclusive. Just a couple of examples working with these types of functions. In exercise A, we're asked to find the sine of sine inverse of -1/2. All right, so we might say, well, can we use those inverse properties? And in fact, yes, we can. For this first example, notice that since x is between -1 and 1, sine of sine inverse of x is then equal to x, and so then this would be -1/2. Now, if you didn't remember that, the other way to look at it would be think of this sine inverse of -1/2. Think of this as being an angle. What angle, sine of what angle is equal to -1/2, where that angle, y, must be between -π/2 and π/2. Well, let's see. The sine of what angle is -1/2, so that's in the sense in the fourth quadrant, or the negative first quadrant, if you're thinking if you're thinking about the direction. And so then that angle would be -π/6, and so then we can think, okay, well then what's the sine of -π/6? And of course then that's -1/2. All right, let's look at one in the other direction. Here we have sine inverse of sine of 5π/6. And the question is, well, can I just do something similar to the previous one? Can I just say, well, this is 5π/6? All right, that's the big question. Well, it doesn't work as nicely in this case because that 5π/6 is not in that restricted domain that we're concerned about. Remember from the previous slide that sine inverse of sine of x is equal to x only if x is between negative pi over 2 and pi over 2. So it's not 5 pi over 6. But we can simply evaluate the sine of 5 pi over 6. And so then this becomes sine inverse, and the sine of 5 pi over 6 is positive 1/2. And now, let's see, the sine of, now we want sine inverse of 1/2, so we think to ourselves, what angle, right? So now let me switch colors here. The sine of what angle is 1/2, where that angle, y, must be on negative pi over 2 to pi over 2. Well, the angle whose sine is 1/2 and is between negative pi over 2 and pi over 2 is pi over 6. Let's look at a couple more expressions. Here we're asked to evaluate the cosecant of the arc cosine of 3/5. Now this one's not as simple. They aren't, the cosine and arc cosine, they aren't inverses of each other, so we have to work a little bit differently. So here's what I'm going to say. Let's call this some angle. I'll use theta. So then if theta is equal to the arc cosine of 3/5, then using the inverse idea, then the cosine of theta must be 3/5. And so now what I can do is I can draw a right triangle, and I'll call this theta. Now if the cosine of theta is 3/5, remembering that cosine in right triangle trigonometry is the adjacent side over the hypotenuse, so cosine theta is 3/5. And then from the Pythagorean theorem, we know that the remaining side of the triangle would be a 4. So now I want the cosecant of that angle theta. The cosecant of theta, remember cosecant is the reciprocal of the sine, and so that's hypotenuse over opposite. And so then this becomes 5/4. Let's look at another example here, exercise B. We're asked to find the tangent of sine inverse of x. I'm going to use a similar idea here. I'm going to say let theta be equal to sine inverse of x. And remember that when we're dealing with that function, that sine inverse of x, that x must be between negative 1 and 1. If theta is sine inverse x, then sine of theta must be x. I'll draw a right triangle. Here's my theta. And the sine of theta is x. Well, I'll think of that x as an x over 1. Sine is the opposite over the hypotenuse. Using the Pythagorean theorem, I can solve for the remaining side of the triangle, yielding the square root of 1 minus x squared. And so then the tangent of theta, tangent is opposite over adjacent. The tangent of theta would be x over the square root of 1 minus x squared, as long as x is between negative 1 and 1. So now let's get into the calculus. Suppose we wanted to differentiate the function y equals sine inverse of x. Alright, so recall that, remember our x values must be between negative 1 and 1, and our y values, the range, must be from negative pi over 2 to pi over 2. And our goal now, remember, if we want to differentiate this, we want dy dx equals something. Well, we don't know the formula yet, so we have to use a little trickery to get there. So if y is equal to sine inverse of x, then, using an idea like I just did in the previous exercises, I can rewrite this as the sine of y is equal to x. And now I can differentiate both sides of the equation, applying the differential operator d by dx to both sides. All right, so d by dx of sine y is d by dx of x. Alright, so d by dx of sine y, I'm going to have to apply the chain rule there. That would be the cosine, right? The derivative of sine is cosine, so I'd have cosine y times chain rule dy dx, and the derivative with respect to x of x is simply 1. So then dy dx is equal to 1 over cosine y. Well, if sine of y is equal to x, let's sort of take a sidetrack here. If sine of y is equal to x, I can draw a right triangle. If sine of y, let's say that that's my angle y, and sine is the opposite over the hypotenuse. So sine of y is equal to x, so that would be an x over 1. Remaining side is 1 minus x squared from the Pythagorean theorem. Then the cosine of y would be the adjacent over the hypotenuse, and so then dy dx would be 1 over, and again the cosine of y would be the adjacent over the hypotenuse. That would be the square root of 1 minus x squared over 1, and so then dy dx is equal to 1 over the square root of 1 minus x squared. Let me show a slightly different approach. And let's go from that point again. So here we know, again, that we've gotten to the point that dy dx is equal to 1 over cosine y. And I'm going to take a slightly different approach than using the reference triangle. That's what we call it. Let's use identities. I know that sine square y plus cosine square y is equal to 1. So then cosine square y is equal to 1 minus sine square y. Well, we saw earlier that sine y was x, so I can make that substitution then that cosine square y is 1 minus x squared. And so then cosine y, applying square roots, would be positive or negative square root of 1 minus x squared. But now wait a second. We know that y is on the interval negative pi over 2 to pi over 2. And since y is on that interval, the cosine of y then must be greater than or equal to 0. And so we can exclude the negative root, and we can say simply that the cosine of y must be equal to the positive square root of 1 minus x squared, and we get the same result as we did before, that dy dx is equal to 1 over cosine y. Sorry, I should have made that substitution. Dy dx is 1 over the square root of 1 minus x squared. So we have now a formula that calculates the derivative of sine inverse of x. If y is sine inverse x, then its derivative dy dx is 1 over the square root of 1 minus x squared. However, whichever approach you want to take. So here's the next example. We're going to differentiate y equals tangent inverse of x. But now would be a great time to pause and try this one out on your own, using the techniques that we just saw in the previous example. Let's take a look at it. If y is equal to tangent inverse x, recall then that x can be any number. X is anywhere on negative infinity to infinity, and y then is on negative pi over 2 to pi over 2. And if y is equal to tangent inverse x, then I can write that tangent of y is equal to x. And I'm going to draw my reference triangle. Here's y. And if tangent of y is equal to x, then let's see. Tangent is opposite over adjacent, so this is x over 1. And then the Pythagorean theorem tells me then that the hypotenuse is the square root of 1 plus x squared. Applying the differential operator, I'd have d by dx on both sides. So d by dx of tangent y is equal to d by dx of x. The derivative with respect to x of tangent y, well, let's see, the derivative of tangent is secant square y times chain rule dy dx equals, and the right hand side is just 1. So then dy dx is equal to 1 over secant square y. Hey, I can simplify that. Dy dx is equal to cosine square y. So let's see, cosine of y from my reference triangle, the cosine of y would be the adjacent over the hypotenuse. And so then cosine square y would be that whole thing squared. And so then cosine square y is equal to 1 over 1 plus x squared. So then dy dx is equal to 1 over 1 plus x squared. If you used identities instead of the reference triangle, you'd get the same result in the end. So we now have a formula for differentiating the tangent inverse function, and then the derivative of tangent inverse of x is 1 over 1 plus x squared. So for your reference, here is a table with the derivatives of the inverse trigonometric functions. We did the sine inverse and the tangent inverse. As part of this presentation, but here are the others. D by dx of cosine inverse of x is negative 1 over the square root of 1 minus x squared. The derivative of the cotangent is negative 1 over 1 plus x squared. So notice how those are related to the ones we did. And then the cosecant and the secant inverse functions are also, I hope you can see that they are related. So it might be good practice to try and come up with those derivative formulas on your own. Let's practice calculating derivatives using what we know. We wish to find the derivative of each function, simplify where possible. The first function that we're given is y is sine inverse of x to the fourth. Alright, so it's not just sine inverse of x, it's now sine inverse of x to the fourth. Alright, so then y prime would be, now let's see, the derivative of sine. Alright, so let's recall from the previous slide, d by dx of sine inverse of x, that is 1 over the square root of 1 minus x squared. But we don't just have an x now, we have a u, right? We have this x to the fourth. So I'd have y prime would be 1 over square root of 1 minus, I'd have the x to the fourth square. But now wait a second, I have to remember the chain rule. So times d by dx of x to the fourth. And so then let's see, y prime would equal 1 over the square root of 1 minus x to the eighth, and then the derivative with respect to x of x to the fourth is a 4x cubed. And so then what I would write, simplifying this slightly, I would say y prime is 4x cubed over the square root of 1 minus x to the eighth. Alright, exercise B, we have y is sine inverse of 2x minus 1. And we're again asked to differentiate or find the derivative. So using a similar idea, I'd have then that y prime is equal to 1 over the square root of 1 minus quantity 2x minus 1 square. And then I'd have the derivative with respect to x of 2x minus 1 from the chain rule. Now let's see, 2x minus 1 square. Oh, I know how to deal with that. Y prime would equal 1 over square root of 1 minus 2x minus 1 square, that's 4x squared minus 4x plus 1. Derivative with respect to x of 2x minus 1 is 2. So let's see, I can work with this a little more. I'd have y prime is equal to 2 over, let's see, I'd have then the square root, after we simplify some things here, I'd have a negative 4x squared and a minus 4x. Oh, plus 4x, sorry about that. Now I can actually simplify this further. So notice I can write that as y prime is equal to 2 over, and I'll write that square root as, let's see, notice I can factor out a 4. So I've got the square root of 4 times, and I'm going to write this as x minus x squared. So I changed the order a little bit, but it's equivalent to what I had. And recall, one of our properties of radicals says that if I have the square root of a product, I can break that up. So I'm allowed to break up that radical as a square root of 4 times a square root of x minus x squared. And so then y prime is equal to 2. The square root of 4 is 2. And then I'd have the square root of x minus x squared. Those 2's reduce out, and I have y prime is equal to 1 over the square root of x minus x squared. And so that's a simplified form for that derivative. Exercise C has us finding the derivative of f of x is cosine inverse x over x. I've got division here. I'm going to have to use a quotient rule. Alright, so let's see. F prime of x would equal, let's see, the low function, the bottom function is x, and then I'd need the derivative of the top function. Cosine inverse x, its derivative is negative 1 over the square root of 1 minus x squared, minus the high function, the top function, cosine inverse of x, times the derivative of the lower function. The derivative of a plane x is 1, and then I would have the denominator square in the denominator. Alright, so now let's see, can we clean this up a little bit? I see that I don't like fractions in fractions, so what I would do is I would multiply both numerator and denominator by the square root of 1 minus x squared. So then f prime of x, I would have negative x for the first term, and then minus cosine inverse of x times the square root of 1 minus x squared. And then in the denominator, I'd have x squared times the square root of 1 minus x squared. Exercise D, we have h of x is x times tangent inverse of x. A product rule. So h prime of x, I like to leave the first part alone, so x times the derivative of the second factor. The derivative of tangent inverse is 1 over 1 plus x squared, plus differentiating the first factor, x, the derivative of x is 1, times leaving the second factor alone. And so we can write that as x over 1 plus x squared plus tangent inverse x. Alright, let's calculate some integrals. Here we're asked to evaluate the integral of tangent inverse x over 1 plus x squared. And I look at this and I say, well, that over 1 plus x squared, that reminds me of the derivative of tangent inverse. So actually, this is a fairly straightforward substitution. If we let u equal tangent inverse of x, du is equal to 1 over 1 plus x squared dx. And so then notice that I've got that 1 over 1 plus x squared dx. So that's the du, and the tangent inverse of x is the u. So this becomes simply the integral of u du, and so that's u squared over 2 plus a constant. And so then going back in terms of the original variable, I'll have tangent inverse of x squared over 2 plus a constant. Integrate from 0 to pi over 2 sine x over 1 plus cosine square x dx. Alright, so for this one, I look at that denominator. See how that denominator sort of looks like we have something over a 1 plus u squared? So I'm thinking, when I integrate this, I'm going to get a tangent inverse. And it looks like if I were to make this substitution, right, that's my substitution right there, I would let u equal cosine x. If I let u equal cosine x, then du is negative sine x dx. And so then let's see what happens when we make that substitution. Alright, so then if u is equal to cosine x, if x is 0, remember this is an x equals 0, this is an x equals pi over 2. If x equals 0, then u would equal 1, the cosine of 0 being 1. And if x is pi over 2, the cosine of pi over 2 is 0. This would be u equals 0. I've got this sine x dx. Well, let's wait a second. I would have needed to throw in a negative, right? I need a negative sine x dx. So there's the du. But if I brought in that one negative, I have to bring in another negative to counterbalance it. So let's remember that negative. And then I'd have a 1 over, my substitution was u equals cosine x, so I'd have a 1 plus u square, and as we mentioned, the negative sine x dx, that's the du. Recall that one of our properties of integrals says, if we're going from u equals 1 to u equals 0, we're allowed to flip the limits of integration and bring in another negative. So I can rewrite this as the integral from 0 to 1 of 1 over 1 plus u squared du. And basically those negatives, I flipped the limits of integration. That brought in another negative which countered this negative. Alright, so now we have then the antiderivative of 1 over 1 plus u squared. Well, that's just tangent inverse u, and evaluating from 0 to 1. And so then this becomes tangent inverse of 1 minus tangent inverse of 0. Alright, the angle whose tangent is 1 on negative pi over 2 to pi over 2 is pi over 4. The angle whose tangent is 0 is 0. And so then this becomes simply pi over 4. We're asked to evaluate integral of dt over the square root of 1 minus 4t squared. Well, gosh, this sort of reminds me, here's what I know. If it was 1 over the square root of 1 minus u squared du, then that would become a sine inverse of u. And so it looks like I should make the substitution. I should let u equal, let's see, I need u squared to be 4t squared. I'm going to let u equal 2t. Because if I let u equal 2t, then u squared is 4t squared, isn't it? And if u is 2t, then du is 2 dt. Alright, so let's see. I need to bring in a 2 here. And so then I would need a 1/2 outside the integral. Alright, and the 2 dt now, there's my du. Alright, so this looks like it's going to work. So then I'd have 1/2 integral of 1 over the square root of 1 minus u squared du. So then this becomes 1/2 sine inverse u plus a constant. And so then, remember, we want to go back to our original variables. 1/2 sine inverse 2t plus a constant. We're asked to integrate from 0 to root 3 over 4 dx over 1 plus 16x squared. Well, here's what I know. If I had the integral of 1 over 1 plus u squared du, that would go to tangent inverse of u. So it looks like, this looks pretty close, it looks like I need to make the substitution u equals 4x, because then u squared would be 16x squared. And if u is equal to 4x, then du is equal to 4 dx. So let's see, I'd need a 4 dx, and so I need a 1/4 outside the integral. 4 dx, there's my du. Remember that that my limits are in terms of x, so I've got x is root 3 over 4, I've got x is 0. Alright, so let's switch that over in terms of u. So I'd have 1/4 the integral. If x is 0, u is 4 times 0, which is 0. And if x is root 3 over 4, multiplying that by 4, u is root 3. Then I'd have a du over 1 plus u squared. So then this becomes 1/4. I've got the du over 1 plus u squared. The antiderivative of that is tangent inverse u from 0 to root 3. So then this becomes 1/4 of tangent inverse of root 3 minus tangent inverse of 0. The angle whose tangent is root 3, maybe from your unit circle if you remember that from trigonometry, would be pi over 3, and tangent inverse of 0 is 0, and so then this gives us pi over 12. Evaluate for a is greater than 0 the integral of 1 over the square root of a squared minus x squared dx. This sort of looks like a sine inverse. Sort of. Remember our rule for sine inverse, it had to be the integral of 1 over the square root of 1 minus x squared dx. And then that went to sine inverse of x. So this sort of looks like it, but we've got that a squared. Well, let's see what we can do with that. We'll use a little bit of algebraic manipulation. I'm going to use some factoring. It doesn't look like I can factor, but I'm going to write that as a squared times, so I've got that square root of a squared times 1 minus x squared over a squared. And this is legitimate. If I were to multiply that a squared back into it, I'd have a squared times 1, which is a squared, and then a squared times x squared over a squared is back to x squared. And now using that same idea as we saw previously, I can now rewrite this as the integral of 1 over, and since I've got that square root of a product, I can break that up. The square root of a squared is a, and I'd still have the square root of 1 minus x squared over a squared. This is still dx. And I can bring that factor of a outside. And so I can write this as 1 over a integral 1 over square root of 1 minus x squared over a squared dx. Now, I think hopefully you can see the substitution you need to make. If we let u equal x over a, then du is 1 over a dx. And so then I'd have 1 over a. I'd have the integral. Now let's see, I need a 1 over a dx. So actually what I'm going to do is let's go back a moment. Let me bring that 1 over a back inside the integral. So if I take this 1 over a that I had brought outside the integral, and if I move it back inside, then notice I have my 1 over a dx. There's my du. And so then I have simply the integral 1 over the square root of 1 minus u squared du. Well, that's an easy integral. The antiderivative is sine inverse of u plus a constant, and then put that back in terms of the original variable. And so that's sine inverse of x over a plus the constant. So we now have a new formula that we can use all the time. So this will work for any value of a greater than 0. So let's rewrite this. This formula becomes important. It's one that we want to probably memorize. The integral of 1 over the square root of a squared minus x squared dx is equal to sine inverse of x over a plus a constant. So this one's kind of similar to the previous exercise. Why don't you take a moment and try this one out on your own? We're asked to evaluate the integral of 1 over a squared plus x squared dx. And I look at this and I say, this sort of looks like a tangent inverse. It's not exactly right, it sort of looks like it. So let's manipulate things a little bit. I'll use that factoring idea. I can write the denominator as a squared times 1 plus x squared over a squared. I can take that 1 over a squared outside the integral. Now this looks closer to a tangent, an arctangent, an inverse tangent. Let's make the substitution. U equals x over a, with du then equaling 1 over a. So 1 over a dx. So let's see, I'll bring in a 1 over a. I've got the 1 over a dx now. But now if I do that, I'd have to multiply it by an a on the outside of the integral. So then this integral becomes, let's see, a over a squared, that's a 1 over a integral of 1 over 1 plus u squared du. That's 1 over a tangent inverse u plus a constant, and then put it back into the original variable. That's 1 over a tangent inverse x over a plus a constant. And again, let's restate that formula because it is a good one to know. The integral of 1 over a squared plus x squared dx is 1 over a tangent inverse x over a plus a constant. All right, that concludes this presentation.